My name is Supriya, and I'm a principal engineer in Last Mile at Amazon. Last Mile is the last leg of delivery in Amazon logistic operations, which means deliveries that happen from a delivery station to the customer's house. The Last Mile team manages all the software and applications that are needed to make that last leg of delivery happen. Last Mile provides deliveries for various different programs within Amazon, like Amazon.com, Whole Foods, and Amazon Fresh. In this talk, I'm going to focus on the problem of anomaly detection in operations and logistics and how Last Mile is solving this problem and some of the future challenges that we are looking to solve. So let's start with what is an anomaly? Any time that the situation changes from what we were expecting or what was planned and what is actually happening is what we define as an anomaly. So, as an example, a damaged package which got damaged during transit is an example where that package needs to be repackaged or a refund needs to be issued to the customer. Another example of an anomaly is a weather condition like floods, which impact a station or the whole area. All of the operations that happen in the delivery station are delayed. Another example of anomaly is traffic. So, any unexpected traffic event could cause a route and a driver to get delayed, which means the packages in the van won't get to the customers on time. So, what makes this problem challenging for Last Mile? Last Mile today in North America has hundreds of delivery stations delivering millions of packages with the help of thousands of drivers. At this scale, the problem with anomaly detection is that without any technical solution, the way anomalies were being detected was either a station manager or an operator looking through dashboards to try and figure out if there is a risk of something going wrong. And this process does not scale as the number of stations, number of packages, number of routes increases as Last Mile grows bigger. We want to be able to do early intervention for any issues because that will help us put in mitigations that can reduce the impact of that problem. And that is another thing which is hard to do when the problem is being detected by manual work, by people looking at dashboards. And both of these are bottleneck for expansion. So we cannot scale if we cannot manage unexpected events or problems and risks effectively. So the strategy that we've taken in Last Mile to solve this problem is to move away from this process of station managers and operators looking at dashboards and metrics to see what may go wrong, and instead move to a paradigm where we surface risks or anomalies to the operators where we believe that it needs their attention. This allows the process to scale. The other big benefit that it allows us is it gives us the ability to centralize a lot of these processes such that one operator can eventually manage multiple stations or areas, and operators can specialize in managing certain types of anomalies and can do them for a wider network than just one station. So to solve the problem, basically we had two goals. We wanted to automate detection and resolution of anomalies as much as possible, and we want to minimize manual intervention. Note that I say minimize and not remove, and that is because at the end of all of this are physical operations. Even though we may automate the detection and as many actions as we can, for resolving a problem, they may need manual actions like putting on a new label or repackaging or moving a box from one area in the delivery station to another for a different process. So, how do we do this? The problem can be thought of in two parts. The problem of detecting a risk, which is based on either input from people or from the systems that are tracking deliveries and tracking different processes, or even from other external data sources. We want to find out when things go wrong automatically. And the second part of the solution is to do resolution tracking, which is we want to track that all the actions that we are taking for that risk are actually mitigating the risk. The core pieces in an anomalies lifecycle start with defining the problem, which is we need to be able to define what constitutes an anomaly. What is its severity? What is its criticality? Once we have the problem definition, we can use events which can either come from, again, manual detection or from systems, planning and execution systems, to be able to detect if that condition is happening. And if that's the case, that's when we know that we have a risk condition or an anomaly. The next step for us is to be able to take some actions to try and resolve or mitigate it. And the actions could be things like informing the customer if we believe that there's going to be a delay, taking actions like reassigning the route to somebody else, being able to send a rescue driver to help a driver who's maybe stuck in traffic or is running behind on their route. Those actions should eventually lead to problem resolution. So let's talk about the architecture and the various components that make this happen. We can think of the architecture in four different parts. The first one being event ingestion. Event ingestion is when we consume events from various systems and applications to be able to find out if there is a condition where there is some risk to a package or to a route or processes in a station. And there are two interesting technical challenges to event ingestion. The first is normalization, which is because we consume data from many sources, we want to be able to convert all of the data that we get into a common format such that the rest of the pipeline does not need to worry about the type of anomaly or the type of event. The second is aggregation. A lot of types of risks that we want to detect require us to aggregate the data or events that we are getting in a way that we can then further figure out if there is a risk. The second part of the architecture is the rule engine. And this is where the automated detection is happening. To be able to find that an anomaly has happened, we need the definition and we need to take the events that we are getting and see if it meets the criteria for a risk or an anomaly. The third part in the architecture is anomaly storage, which is where we track all the anomalies that have been detected and also track the resolution of them and what state the resolution is in. And the last piece of the architecture is the operator-facing tools that manage things like assignment of an anomaly to a station manager or an operator where we believe that they should take an action, as well as visibility and reporting tools. The reason why we need an assignment engine here is because the fleet of operators also changes throughout the day and during various times of the year. What we want is the ability to effectively load balance that across operators as they come on duty and go off duty. Next, I want to talk about some key learnings that we got from running this architecture for last mile. Anomalies need to be actionable. They need to be such that they can be acted upon and resolved, whether through automation or through manual actions. We only want to surface to operators or station managers things that they can act upon, which is where we had to differentiate between what is an anomaly versus what is a metric or a report. The other learning was that we don't want any intrinsic delays in the architecture on its own. This is because we want early intervention and we want to identify problems as early as possible to be able to efficiently resolve them and minimize the impact that they may have. The third learning was being able to have anomaly definitions. As last mile grows and as the number of programs that it supports increase, we don't want the architecture to understand each type of anomaly because that will become a bottleneck as we want to add more types of detection and resolution. And the ability to define an anomaly comes into picture then such that the architecture in itself does not need to know the difference between one or the other anomaly. It just needs to know the logic it needs to execute to be able to detect it. And the last learning is to have a task-based approach where we treat anomalies as tasks that can be assigned to operators and can be tracked. And this centralized workflow allows us to load balance the work across our team of operators or station managers. It also allows us to prioritize anomalies based on their risk and how big the risk is. This system today in North America manages about 1.5 million anomalies a day. And out of that, about 370,000 anomalies require manual actions. One of the next pieces that we want to focus on now is Action Engine. Last Mile today has about 370,000 anomalies that require manual intervention. And as our operations grow and as our complexity increases, we are running into cases where for detecting or resolving a problem, we need a mix of virtual actions that could be automated and physical actions like moving a package. To be able to do this effectively, we have a need for building an action engine that can track various actions that are required to solve or mitigate a problem, where these actions are a mix of both digital or virtual actions as well as manual actions. The other interesting piece that's coming up for this architecture is moving away from the rule-based learning to more a machine learning-based exception detection. Because again, as we scale, we want to get smarter about risks because there are various factors that can contribute to operations being impacted. I hope this talk gave you a good insight into last mile, as well as the problem of anomaly detection and how last mile is handling it. Thank you.